If you've ever trained a large language model, you've probably hit the same wall: sequence length. Double the context, and your memory usage doesn't just double. It quadruples. And that's not a bug. It's baked into the math of how modern AI actually thinks. Today, we're going to unpack exactly why self-attention scales quadratically, what that means for inference and training, and how researchers are rewriting the rules to break that bottleneck. Let's start with the foundation. The transformer's core mechanism is self-attention. For every token in a sequence, the model computes a dot product between that token's query vector and every other token's key vector. Those raw scores get softmaxed into weights, which then multiply the value vectors to produce the output. It's elegant, it's parallelizable, and it's O of n squared in both time and memory. Why? Because you're building an n by n attention matrix. Every token needs to attend to every other token. At 20,000 tokens, that's 400 million pairwise interactions. At 100,000, you're looking at 10 billion. The memory footprint isn't just heavy, it's prohibitive. But here's where it gets interesting. The quadratic cost isn't just theoretical. During training, you're storing activations for backpropagation, which means the full attention matrix has to live in GPU memory. During inference, you're generating token by token. Each new token needs to attend to all previous tokens, so you keep caching the key and value vectors. That's the KV cache. It's brilliant for speed, but it grows linearly with sequence length, and since each layer stores it, you're multiplying the problem across the entire model. A 70 billion parameter model with 100 layers and a 50,000 token context can easily burn through hundreds of gigabytes just on cache. Researchers didn't just accept this. They attacked it from two angles: optimization and architecture. On the optimization side, you've got FlashAttention. It's not a mathematical hack. It's a memory-aware algorithm that restructures how attention is computed. Instead of loading the full attention matrix into high-bandwidth memory, FlashAttention processes it in tiles that fit in on-chip SRAM. It computes the softmax in two passes, tracks running max and normalization factors, and only writes intermediate results when they're strictly necessary. The result is the same output, but with linear memory complexity relative to sequence length, and a massive speedup because you're no longer bottlenecked by HBM bandwidth. It's become the default in almost every modern training framework. But optimization only gets you so far. The real paradigm shift is happening in alternative architectures that abandon the quadratic attention matrix altogether. Enter linear attention. The trick here is algebraic rearrangement. By applying a kernel approximation to the softmax, you can swap the order of summation and matrix multiplication. Instead of computing n-squared interactions, you compute a fixed-size summary of the sequence, then project the new token onto that summary. Memory scales linearly. Speed scales linearly. But you lose some of the exact pairwise modeling that dense attention provides. It's a trade-off between fidelity and efficiency, and it works exceptionally well for long context tasks where global structure matters more than fine-grained token interactions. Then there's the state space model family, with Mamba leading the charge. Mamba drops attention entirely and replaces it with a selective recurrent structure. At each step, the model updates a hidden state by mixing the new input with a previous state through learned, input-dependent gates. It's inspired by classical control theory, specifically continuous time systems discretized for neural networks. The key innovation is selectivity. The model learns to forget irrelevant history and retain critical context, all while maintaining constant memory complexity per step. During training, you can still parallelize across the sequence. During inference, it's strictly linear. You don't cache a growing matrix. You just carry forward a fixed-size state vector. It's not a silver bullet. Attention still wins on tasks requiring precise, long-range dependency tracking. But it's a serious contender for ultra-long context, real-time streaming, and edge deployment. So where does that leave us? The quadratic bottleneck isn't disappearing overnight. Dense attention remains the gold standard for reasoning, code generation, and tasks where exact token-to-token relationships are non-negotiable. But for retrieval, summarization, audio processing, or any application where context windows stretch into the hundreds of thousands, the alternatives are already shipping. The future isn't about picking one architecture. It's about hybrid routing. Models that dynamically switch between dense attention for critical reasoning blocks and linear, or state-space paths for long-range context. Some researchers are even exploring sparse attention patterns that only compute interactions for semantically relevant tokens, pruning the matrix in real time. If you want to dive deeper into how these architectures actually perform under load, or how to benchmark memory usage across different sequence lengths, I've linked the key papers and open-source implementations in the description. The field is moving fast, and the next breakthrough won't come from scaling parameters alone. It'll come from smarter computation. Let me know which architecture you think will dominate the next wave of long-context AI, and I'll see you in the next one.